have any questions, or if you want to use any of my slides, my email is up there, and I'll bring it up again at the end. So this is part of the fire and water presentation that a few people mentioned. I'm going to talk about how climate change is impacting extreme weather in California. And so we found this is a really effective way to kind of introduce a CCL solution, because a main problem is that people don't really realize the urgency of the problem. So when people are surveyed and they're asked, is climate change impacting you? Most people say no. And so they view it as a problem that's distant in time and space. It's going to impact somebody else in the future. It's not going to impact me. And so they don't view it as an urgent problem, and so they don't base their votes on climate change, and so then policymakers don't have to worry about not doing anything about climate change. And so it's really useful to actually show people how climate change is impacting them. And so as Californians, this is how we do it. Just some quick background about me. I got degrees in physics and astrophysics, and then I shifted over to environmental science and started researching climate change in 2006. And I started writing about it for the skepticalscience.com in 2010 and the Guardian newspaper about 2 years ago. And I've published a few peer-reviewed climate papers. For some reason that's in black text, but I've published a few papers. So I like to say that I'm not a climate scientist, but I'm kind of like the next best thing if you can't find a climate scientist to talk to. And of course I'm a member of the Sacramento chapter. And very exciting for me, I just literally like 2 days ago got a book published. So it's about climate science and climate myths and some history and stuff, and it also talks about the future and about solutions, and it's got a big section on citizens' climate lobby. So, you know, go buy it on Amazon, right? So, the title is, you can search for climatology versus pseudoscience, that's the title, or you can search for my name and it pops up on Amazon, and I would appreciate it if people would buy the book and tell people about it. So, quick plug for Skeptical Science, because this is like the best website to go to. It's like the best website to go to if you want to learn about basic climate science and climate myths. If you hear a climate myth and you want to know why it's wrong, what we do is we look at the peer-reviewed scientific literature, and then we kind of put it into simple terms that everybody can understand. And we have this useful feature. If you click on a particular myth, at the top of the page, there's 3 tabs. There's a basic level if you just want like a couple paragraphs and a graph explaining what the fundamental problem is with the myth. We've got that. And if you want more technical detail, you can go to the intermediate tab and the advanced tab and see more technical detail. Yeah, great website. And then that's my blog at The Guardian. It's called Climate Consensus of 97%. And one of my papers that I published is on, we found a 97% consensus in the peer-reviewed literature on human caused global warming, so that's why we made that the title. And I write with my colleague John Abraham. And on Monday I'll have a post on both The Guardian and Skeptical Science about my book. So that's a good place to get my book. So that was probably enough shameless self-promotion, right? Okay. Oh, there's also a smartphone app at Skeptical Science. So if you got Skeptical Science and go to the bottom right margin of the page, you can click on it and download a smartphone app that has the same myth debunking for Skeptical Science. So a little bit of background, just to set the scene for what I'm going to talk about. So there is at 2 degrees, you can see the red dashed line across the middle. That's the 2 degrees they call kind of the danger limit. It's kind of the internationally accepted. We don't want global warming to go beyond that level because it's very risky if it does. And so this is, you are here, we're right there. And then this is 4 different scenarios that the IPCC, the latest report, looked at. And so the purple and the green are kind of business as usual, lots of fossil fuel badness. And the red is if we take a little bit of action or some moderate action to reduce greenhouse gas emissions, and the blue is if we take a lot of immediate action to reduce greenhouse gas emissions. And so you can see the blue one, immediate action, immediate serious action is the only one that stays below that danger limit. But there was actually, in the panel last night, somebody asked a good question. When will it be too late? Or how much time do we have left? Yeah, how much time do we have left? And so my answer to that question is, it's never really too late because the problem could always get worse. And so, you know, if we miss that, if we go past that 2 degree line, the world's not going to end. So like 2.5 degrees isn't as bad as 3 degrees, which isn't as bad as 3.5 degrees. So even if we miss this 2 degree level, it's not the end of the world. It could always be worse. We could always make the problem less bad. But these are the 4 scenarios the IPCC looked at, and I'm going to kind of return back to these. So remember the 4 lines, especially the the red, the blue, and the purple.
Dana, can you lower the screen or raise your image because we can't see the dates?
I can't really change it, but so it goes from 1900 to 2150 at the end. So, global warming. This is California temperature, surface temperature in California, and so you can see this is a long-term warming trend in California, just like the rest of the planet. In 2014, we shattered the previous record. 2014 is way up here. So it was like, I think, a full degree Celsius above the previous record. Shattered the previous record. So we've had a lot of warming in California, as with the rest of the world. And that has a lot of various climate change impacts. And so one of the impacts is on the Sierra snowpack. And so this chart's from a paper that was, I think it hasn't been published yet, but it was just reported on in the Sacramento Bee. And it's from the Scripps Institute of Oceanography. And they were looking at how global warming will impact the Sierra snowpack. And the Sierra snowpack is really important because that's where it's kind of California's natural water storage system. So as the Sierra snowpack melts throughout the year, it refills our reservoirs. So very important water storage. But they found that, and this is the business as usual scenario, we'll lose a lot of the snowpack over the next century. So at the top you can see each degree Celsius warmer we get, we lose about 25% of the Sierra snowpack. And so, let me see if I have that. Yeah. It's coming back here. We get in the blue sort of best case, take a lot of action to reduce global warming. We only get about 1 degree more Celsius global warming, but if we do the higher business as usual pathways, we get 4 or 5 degrees Celsius global warming. So we could get anywhere between a 25% loss of snowpack, which is a lot, but it's manageable, it's something we could live with, to basically losing the entire Sierra snowpack, which would be very, very difficult for us to adapt to. So that's just one example of the importance of taking action to reduce the problem so that we don't face really, really bad impacts. There's a big difference between taking action and not taking action in terms of mitigating the problem.
So I imagine that later you're going to talk about what it means not being able to adapt to, like...
I don't really have time to go into it, unfortunately.
Next time.
Yeah.
Okay. I mean, if it's a matter of turn the tap on, there's one town in the South Valley that they have to go drive 20 miles just to get water to brush their teeth or wash their dishes.
Yeah, I mean, I don't have that level of detail, unfortunately, but yeah, it's just a lot of bad things that happen. Okay. So this is an animation I put together to look at how the California drought has evolved over the past 3 years. And so at the top here, you're going to see the date change, and on the map, you're going to see the colors change. And so white is no drought, yellow to orange is kind of moderate drought, and then the reds are extreme and exceptional drought. So watch that as it changes. So you can see in 2012, 2013, most of the state got pretty moderate drought, and then it just kept on getting worse after that. So most of the state was in extreme drought, and then that really dark stuff, that's called exceptional drought. That's the highest level of drought that they measure. So I haven't updated it since August, but that's what it looked like last August. It doesn't look a whole lot different now. Basically, the entire state is in drought conditions, and a lot of it is in extreme and exceptional drought. You can email me and I'll be happy to send you the slides. And so there was just a couple of months ago a study published where they wanted to put these current drought into historical context. And so what the scientists did is they went through California and they took a whole bunch of tree ring samples. So you can see it looks like that. They kind of drill a core into the trees and look at the tree rings. And tree rings are very good indicators of how much water is available. And so they did that, and this is what the chart looks like. This is the last 800 years of precipitation in California. And so you can see 2014 is right here. Very low precipitation, but it's not unprecedentedly low. You can see there were years in the past where we had less precipitation. And so there was also recently a NOAA report that was kind of misleading about this because they said that the current California drought is just natural because the amount of precipitation, it's basically the same thing as this. They said the amount of precipitation is not unprecedentedly low, it's within the range of natural variation, so it's just a natural drought. So the problem with that is that drought isn't just about precipitation, it's really about water availability. And there's more to that than just precipitation. And so in this same paper, the scientists also looked at a reconstruction of drought intensity. And that's this chart. And so here's 2014 down at the bottom, and it was basically the most intense drought the California's seen in their record. And when they put together 2012, 2013, 2014, it was the most intense drought California's seen in over 1,200 years. And so, the question is, if we didn't get an unprecedentedly low precipitation, what pushed the drought into those record levels? And they concluded that it was the high temperatures, those record temperatures I was showing earlier. Because when you have higher temperatures, you get more evaporation, you get more water demand, you get all these different factors that make the drought worse. And so their estimate was that the high temperatures, it basically increased the drought by about 36%. So it went from a really low water availability due to precipitation to unprecedentedly low water availability because of that global warming impact factor.
That's an important slide.
And then just about a week ago, there was a paper published it was led by Benjamin Cook at NASA, where he was looking, so they talk more about the drought, and so I'm just going to play this video if we can get it to go, and if I can get the sound to go.
A new NASA study predicts that by the end of the 21st century, the American Southwest and Great Plains are likely to experience longer and more severe droughts than at any other time in the last 1,000 years.
So recent droughts, such as the ongoing drought in California or in the Southwest, or even historical droughts such as the Dust Bowl in the 1930s, these are naturally occurring droughts that typically last several years or sometimes almost a decade. In our projections, what we're seeing is that with climate change, many of these types of droughts will likely last for 20, 30, sometimes even 40 years, even exceeding the duration of the long-term intense mega-droughts that characterize the really arid time period known as the medieval climate anomaly.
So how can we peer into the planet's future? Researchers combine natural observations and harness the processing capabilities of powerful supercomputers. The scientists looked at 1,000 years of tree ring data and compared those records with soil moisture data from 17 different climate models in order to extend this drought information into the future. The models all show a drier world thanks to increased temperatures from human-induced climate change.
With these computer simulations, these climate models really represent our best understanding of the physics and the workings of the climate system. They're tested extensively against observations, and at the end of the day, if we want to investigate future climate, they are really the only tool that we have to use.
How bad these droughts are likely to get has a lot to do with how much greenhouse gas emissions humans generate in coming years. Scientists looked at two different possibilities. First, a business-as-usual scenario where worldwide greenhouse gas emissions continue on their current course. In this case, the future risk of lengthy droughts rises to 80%. Alternatively, if the world were to take aggressive actions to reduce emissions, the models still show drying, but the trends will be less severe. In either scenario, droughts could potentially have major impacts in a region already facing water management concerns.
These droughts really represent events that nobody in the history of the United States has ever had to deal with. And so even in the modern era, droughts such as the ongoing droughts in California and the Southwest, these normal droughts act as major stresses on water resources in the region. So we expect that with these much longer droughts, it's going to be even more impactful and cause even more problems for agriculture and ecosystems in the region.
So there were two key charts in that video that went by pretty fast, so I've got them here. So this chart is they called it aggressive action, but it's that red chart that I showed earlier where it's kind of some action, but we can do better than this. If we, if CCL can get carbon fee and dividend passed, we can do better than this. But this is if we take some action and so you can see basically browner is worse drought, blue is more precipitation. So this gets pretty bad, but it's adaptable, it's more drought, but we can probably live with it. But we can do better than this, but it's not so bad. The business as usual. So this is the business as usual case. That's really bad. So you can see, so that's California there, obviously. That's what we call the Midwest breadbasket. So these are major agricultural regions seeing extreme drought. A lot of the time we're talking mega droughts that last for decades potentially. So there's a really big difference between taking some action and taking no action. And so I also want to talk about the cost of drought because that's a good idea. So when people talk about the cost of climate change, they usually talk about the cost of doing something, which we at CCL know, doing something about climate change doesn't have to cost a lot of money, but that's what people usually focus on, and they don't really focus on the cost of not doing anything. And so this table is from a report published by UC Davis, where they were basically anticipating how much a drought from 2014 will cost the state. And put it all together, they said it's going to cost the state $2 billion, and that's a really big bill. So again, the reason I bring this up is because it's the problem of not doing anything has really big costs, and it's having costs right now. It's not costs that are going to happen in 100 years. It's stuff that's happening to us right now, right here. It's immediate, and it's a big problem.
Is that 2.2 billion? Which year?
This year, 2014. It's for the 2014 fiscal year, I think. So when you have drought conditions, it also creates conditions that are ripe for big wildfires. So there's a connection there. And so this chart is for the western United States. It's large wildfires, which are 1,000 acres or bigger in size. And it's from 1970 to about 2010. You can see there's a big upward trend there. And I mean, that's not all due to climate change. There's other issues like forest management, things like that. But again, when you have hotter, drier conditions, you also have conditions that are going to create bigger wildfires. And so this chart's from a paper published in 2011 where they were trying to look at exactly, under various different global warming scenarios, how much will it impact wildfires in California. And so this is the business as usual high greenhouse gas emissions scenario. Anything from red and above is at least a doubling in the area burned by forest fires in a given year in 2085 as compared to 1975. And so you can see for Northern California especially, wildfires are a really big concern, especially in the Sierra Nevadas, and then for those of us who live in the valley, we get the air pollution from the wildfires, and that causes all kinds of health problems from breathing the pollution. And so, they also looked at in a scenario where we reduce gas emissions, what does it look like? And if we again take serious action, it's still an increase in wildfires, but it's less than half of the increase that we see in the business as usual. So again, a very big difference between doing something now and letting it happen in terms of climate change impacts and impacts to health, and firefighting, and the cost of firefighting, and dangers to firefighters' well-being, and all those factors.
What paper is that?
Oh, I don't have the name on it.
Okay.
If you email me, I can give you the name of the paper. So, the question is, the main reason that we've been getting so little precipitation is this thing off the coast called the Ridiculously Resilient Ridge. Super awesome name, right? So it's this high pressure ridge sitting off the coast right there. It's been sitting there for basically 2 or 3 years. And it's a high pressure ridge, so when you get a storm coming in, it pushes the storm up to the north and into sort of Alaska, Canada, and basically away from California. And so we haven't been getting very much precipitation. And so there is a question, is that ridge connected to climate change? Human-caused climate change in any way? And so there is a possible connection with the Arctic, actually. And so in the jet stream, normally the jet stream goes from west to east across northern North America, but sometimes it gets these wavy patterns, looks like that. These wavy patterns, they're called Rossby waves. And so one of the contributing factors to why we get these wavy patterns is the temperature difference between the Arctic and lower latitudes. And so when there's a big temperature difference, that kind of acts as a force to hold the jet stream in place, and you get more straight patterns as opposed to more wavy patterns. But the Arctic is actually, while it's obviously a really cold region, it's actually the fastest warming region on the planet. And so when the Arctic warms, suddenly you get less of a temperature difference between the Arctic and lower latitudes, and you get more of these wavy patterns, and potentially you get more ridiculously resilient ridges too. And I think I have a video about that. So the reason the Arctic is warming so fast is because there's so much sea ice in the Arctic, except the sea ice is disappearing. And so when you have sea ice, sunlight bounces off the ice, goes back out into space, and keeps it cool. When the ice melts, suddenly you have dark oceans that are revealed on the Earth's surface, and the dark ocean absorbs the sunlight and causes it to warm faster. And so we call that a positive feedback, because you get warming that causes an effect that causes more warming. And so, like I said, when you get that reduced temperature difference, you get more of these waves. And when you get these waves, weather patterns tend to get stuck between the waves. And so you get more, so this is a paper, Spring and Simmons published a paper in 2014. They found when you have these Rossby wave patterns, you get more extreme temperature and more extreme precipitation and basically between those waves with weather patterns getting stuck. And there's also been a couple papers published now that have said basically the ridiculously resilient ridge, there is a traceable human fingerprints in the intensity of it. Basically natural factors can't explain it, so basically they run climate models with human greenhouse gas emissions and without. And they look specifically at how often these kinds of high pressure ridges form off the coast, and they form a lot more often when there is high human greenhouse gas emissions in the atmosphere.
Is that happening this year too?
The ridiculously resilient ridge I think is still there.
It's there.
So this is a nice video that sort of shows how dramatically the Arctic sea ice has changed over the past 25 years. So the left ice cube, that's the volume of sea ice in the Arctic in 1979, and the right ice cube is going to show how it changes every year since 1979 through this past year. If I can get it to go. There we go. And then the red data in the back is going to show also how it changes every year. So one thing to keep in mind is that the red data, it's really bouncy, you know, it goes up and down, it's got a lot of wiggles because there's natural variability. Sometimes the weather happens to be better in the Arctic for Arctic sea ice to stay in place, and sometimes the weather is better for sea ice to disappear. But the long-term trend is pretty dramatic. So we've lost about 70% of the Arctic sea ice volume in the past 3 decades. And so the past couple of years, there's been a few news stories saying that the Arctic sea ice has rebounded. They're talking about that little bounce right there. So 2012 was one of those years where the weather was just happened to be good for sea ice to be leaving the Arctic, and then the last 2 years, 2013, 2014, the weather conditions weren't so bad. And so we had a little bit of a bounce back, but the long-term trend is obviously very clear. Arctic sea ice is in bad shape. So these dramatic changes in the Arctic are potentially impacting the climate around the rest of the world too. So we can look further back in time. This is a reconstruction of Arctic sea ice coverage over the past 1,450 years. So you can see, you know, there's some wiggles, but overall it's pretty steady until the past 30 years. Again, it kind of drops off a cliff. And so there have been a few studies looking at what's contributing to the sea ice loss, and they did find that there is definitely a human contribution, and humans are probably responsible for most of the sea ice loss over the past 30 years. So to kind of summarize those impacts from climate change on drought, we have the loss of snowpack, and so warmer temperatures. They cause more precipitation to fall as rain, less as snow. And a good example was the latest storm that we got. We got actually quite a bit of rain in California, but the Sierra snowpack, there was very little snow. So it's good for refilling reservoirs for now, but when we get to, you know, the hotter months when we're supposed to be replenished by the snowpack, there's not much snow to replenish the reservoirs at that point. We also tend to get, there's more water vapor in the atmosphere because there's more evaporation. And so you get, when storms hit, you get more downpours basically, but then you get more rain coming off as runoff and less is sort of stored in the soil, which is worse for droughts. You get faster snowmelt throughout the year, and so the snowpack doesn't last for as long. You get more evaporation both from reservoirs and from soil, and so you've got drier soil, that makes the drought worse. And then on top of that, there may be this connection between loss of Arctic sea ice and more of these high-pressure ridges and wavy jet stream patterns causing freaky weather and pushing precipitation to the north. That's a little bit, it's not a sure connection, so these other factors, all these are ways we know that global warming makes California droughts worse, and there may be this additional factor with human-caused climate change impacting the Arctic, which in turn may be impacting California drought too. So that was all kind of gloom and doom, and I don't like to end on gloom and doom, so I got this, you know, positive slide to end on. Because, you know, we saw there is a big difference between doing nothing and doing something. There's a big difference between losing 100% of the snowpack and losing 25% of the snowpack. Or droughts becoming super, super bad, or droughts just becoming a little worse. So, and then there's all these other co-benefits. If we take action, we know we're going to create more jobs, and we're going to have potentially, you know, small benefits to the economy. And so there's a lot we can do, and so it's good to remember that while there could be a lot of bad things happening, we can prevent a lot of those bad things from at least getting really bad. So that's it. There's my information again.